Go away. Hey everyone, I'm Aaron, and today I'm going to be covering asymptotics with y'all. So, as computer scientists, it's your guys' responsibility to understand how fast y'all's functions are running, and the way that we compare how fast and how slow some functions are running are using mathematical notation and asymptotic analysis. So, in asymptotics, there's these bounds that you use to describe how fast your functions are running, and the three bounds that you guys really need to know are big O, big omega, and big theta. So big O, to sum up, is pretty much your upper bound in terms of your input size. It means that your function is going to take this time or it'll be faster than it. So just to draw this out with a little graph over here, so we have an X and Y axis. This is going to be your input. And this will be your time on the Y axis. And we can use this line over here to show our big O bound. Big O means that we're going to have everything underneath this line because we're covering our worst case runtime too. And big omega is pretty much the opposite of this. What it means is that it's going to be a lower bound in terms of your input size. So big omega will cover your best case and all the cases that are slower than it. So essentially it's saying that your function will take this time or it will be slower. Big theta is when your big omega and your big O bounds are equivalent to each other. And what this means intuitively is that your function is running within a constant factor of your bound. And just to complete the graphs, I'll draw one more over here for big O. Oh, big omega, my bad. So that is going to be a lower bound. All right. So the next important tool that you guys need to know in asymptotics are your fun sums. These cover the constant sequence, the arithmetic sequence, and the geometric sequences. These sums are seen all around in asymptotics. They're super useful, and I really suggest putting them on your cheat sheet. So the constant sequences, we're just taking a bunch of constants and we're adding them up n times. So these are n1s in this case, and when you take n1s and add them up, that's just equal to n. For the arithmetic sequence, we're just going up sequentially by a constant. So in this case, we're going up from 1 to 2 to 3 to 4, all the way up to n, and this is equal to n squared. And the final sequence you guys need to know is the geometric sequence, where we go from 1 to 2 to 4 to 8, all the way to n. So in this case, we're doubling the terms in our sequence by a constant, which is 2. And pretty much when determining the runtime of a geometric sequence, we look at the dominating factor or the largest term in our sequence, which is going to be n. And that is what our runtime is equal to in terms of a theta bound. Just for you guys' convenience, we also have the generalized versions of these sequences on the bottom of the slide. Chances are you all won't encounter the most basic ones while solving runtime questions. So it's helpful to have these generalized versions on your cheat sheet too. Okay, so now let's talk about how to solve asymptotics questions. So pretty much asymptotics questions really fall under two categories, and those are recursion and iterative type questions. So let's first cover recursive type questions. And there's three main steps how to cover these. So the first step is that we take a look at our function's body and we try to determine where our recursive calls are. So in this case, we have a function f. It has a base case over here, some work being done in our function g of n, and two recursive calls over here at the bottom. And using our recursive calls, we're going to draw a tree diagram with every single node in our tree representing a function call, and we're going to associate or put our input within that node. So just for example, if I were to draw a tree diagram for this function f over here, I'd start off with a node with input size n. That node is going to have two more recursive calls to f, each with an input size of half the parent. So n over 2 in this case. And then these two children are going to have two more recursive calls also with an input size of n over 4. And this goes on until we reach our base case. So once we've drawn out our tree diagram, the next step is to divide our tree into layers and calculate the work per layer. So in our previous example, we had a tree that looked like this. And if we take a look at our function one more time, we see that the only work that we're really doing in it is when we call g of n, and g of n runs in a constant amount of time. So for every single node in our tree, it runs in constant time. So our first layer has one node, therefore the amount of work per layer done is just one. Our second layer has two nodes, therefore the amount of work per layer or done in the second layer is going to be 2. Our third layer is going to have 4 nodes, therefore we have 4 work done in this. And right now we're counting some sort of pattern. So the amount of work being done per layer is simply just the number of nodes per layer. And the number of nodes per layer can be written as 2 to the power of the level we're at. That should be 1. So originally this is the 0th level over here. This is the first level. This is the second level. So for this question, I'm just going to give you guys that our final level is going to be when we're at log n. Therefore, the amount of work being done at that level is going to be equal to n. And I'll go over a little bit later on as to why our final level is going to be log n. But for now, we have like this sort of sequence where our work per level is just doubling as we go down a level. So now the final step is to take all the work per level that we calculated and just to sum it up together for all the levels. So we had in our first level, 1 work being done. The second level had 2 work being done. The third level had 4 work being done. The next one after that was 8, then 16, then 32, all the way to n over 2, all the way to n. And using some of the summations that we covered earlier, we can determine that this is equal to theta of n, since it is a geometric summation. So previously I mentioned that the final level was log 2 of n. And the reason why is because this is equal to the height of the tree. And in the next slide, we'll go over how exactly do we derive the height of the tree. So a really useful method in trying to like solve these recursive types of problems is finding the height of the tree. And like this is super useful for patterns where we determine that every single level has the same amount of work happening, because then we can determine the total amount of work by just calculating the number of levels and just multiplying it by the amount of work per level. And like sometimes finding the height of a tree is like pretty easy. Like let's say we have some sort of tree that looks like this. It goes from n to n minus 1 to n minus 2 to n minus 3, just decreasing to 1 till 1. Then like we can just take a look at it and be like, oh, it has n levels in it. However, there's definitely cases where it is a lot harder to determine the height of the tree. And one of these really difficult cases is when your input size is constantly halving itself. So this is when our input is going from n to n over 2 to n over 4, all the way down to 2 to 1. So the question is, how do we determine how long the sequence is or how many levels are in it? So we can rewrite it out using the powers of 2, and it becomes a lot easier to determine that. So let's say we start from n to n over 2, all the way down to 2, 4, 2, 1. If we choose to write this in powers of 2, we can rewrite it as this. 2 to the power of log 2n, which goes to 2 to the power of log 2n minus 1. So this is going to be 2 to the second power, 2 to the first power, and 2 to the 0th power. So if we take a look at all these exponents over here, we can see that there's clearly log n levels in our sequence. Therefore, the height of this entire tree is going to be log 2n also. So that's why the length of the sequence is log n. So going back to this last question over here, we see that our input size is constantly halving itself. And that's the reason why the last level is going to be log 2n, because the height of our entire recursive tree is also going to be log 2n. So now let's cover the second type of runtime problems that you guys might encounter, and that is iteration. So to solve iteration problems, you're going to first find your stopping condition, which is usually the middle part of your while loops or for loops. And then you're going to look at your mode of iteration, which is the last part over here. And then you're just going to use these parts and the starting point of your loop to determine like how many iterations are going on in that loop. And a really useful trick for iteration problems is if like the number of iterations in your inner for loop is constant, then you can just multiply the number of iterations in the outer and inner for loops to just get the total number of iterations. So for example, in this inner function over here, or this inner loop over here, we see that j is always going from 0 to n, no matter what the value of I is. So we know that there are j iteration, or they are n iterations on the inner loop. And we know that for every single value of I, we're going to be running our inner loop through completion. So therefore, we have n iterations of our outer loop too. So we can calculate the total number of iterations simply by multiplying them together. Therefore, the total number of iterations in this example is equal to n squared. Now, sometimes in 6U&B, the number of iterations in your inner loops won't always be constant. And in those cases, it's really useful to try and create a table. So for the example below over here, we see that our inner for loop j depends on our value of I, which is changing per every single iteration. Therefore, it's not that easy just by like looking at this code and determining the runtime. So in order to tackle this, we can create a table. So one of these columns is going to have the values of I, and the other column is going to have the amount of work being done for that value of I. So in our first iteration, I is equal to 1. And we're going to enter our second loop over here, and j is also going to be set equal to 1. And we're going to stop when j is less than I. And because j is equal to I, we're actually going to be doing 0 work when I is equal to 1. So when I is equal to 2, j will also start off at 1, and then j will print out hello Tony, and then we're going to increment j to be 2. So we're going to have one print statement being executed in this loop. Therefore, we're going to be doing 1 work. When I is equal to 3, j is going to start off at 1. Then it's going to have a print statement. Then j will increment up to 2. It'll print out 1 more time. And then j will be equal to 3, and we'll terminate our while loop. So we printed out twice, so we've done 2 units of work. And so far, we're encountering some sort of pattern where for every single value of I, we're just simply doing 1 less amount of work. Therefore, we can extend this pattern up to n iterations of I and find the total runtime of our function. So when I is n, the amount of work that we're going to be doing is simply just going to be n minus 1. And then we can take all these values of I and just sum up the work that's associated with them to determine the amount of work for our entire loop. So we're just going to take all these things, write them out. And this is really similar to our arithmetic sequence. So we're just going to use that to get our final runtime. Now, there are some slight discrepancies between this sequence and the one that was shown in the slide. However, they just simply differ by a constant factor. The arithmetic sequence goes from 1 all the way to n. This is just one less than that. And when we're working with runtime, we can simply just drop off constants. Therefore, our final runtime is still going to be n squared. Okay, so let's go over an extra example of this. This one's a little bit more complicated than the last one. So I is going to start from 1, it's going to go to n, and for every single iteration, I is going to be doubling itself. And just like the last example, j is also dependent on I. So let's write our table over here. I is going to be on our left column, the amount of work is going to be on our right. So when I is 1, j is also going to be equal to 1, and we're immediately going to exit out of our loop. So we're going to be getting 0 work done. So in the next iteration, I is going to be equal to 2, and then j is going to be equal to 1. So it'll have one print statement, and then we'll increment j. J will then be equal to 2, and we'll exit out of our loop. So for the next iteration of the outer loop, I will be equal to 4, and then j will have three print statements being done, because j will start off as at 1, it'll print once, then j will be equal to 2, it'll print once, then j will be equal to 3, it'll print one more time, and then finally j will be equal to 4, and it'll exit out of the loop. So we have another really similar pattern where the amount of work that's being done is just equal to I minus 1, or the value of I minus 1. So we can just take that pattern and apply it to all of our values of I and figure out the runtime of our function. So we see that we have some sort of really similar pattern over here to a geometric sequence. However, it is slightly off, and that's all right because it's just off by a constant factor. So we can just change all these values of work, just add 1 to all of them. So that when we sum them up, it's the exact same as our geometric sequence. And the runtime of our entire function is going to be theta of n. And actually, just to be a little bit more specific, there are exactly log n items in the sequence, and we added 1 to every single one of them. So the actual amount of work that we've done is going to be n minus log n. And because this is a smaller factor, we can drop it out. And that'll be it for the walkthrough. We do have 2 more questions that are associated with it, and those will be linked below, I believe. Good luck on the final, everyone.